We've covered maintenance fundamentals and explored business risks from equipment failures. We also examined reliability and its role in any process. At its core, equipment reliability is governed by the physics of failure, which explains material degradation through physical, chemical, and mechanical processes. In this video, we'll dive into its key aspects and applications. Basic failure mechanism. Physics of failures deals with failure at atomic or molecular levels. Physics of failure applied at the component level at equipment. Some example of failures. Whereas the damaging, gradual removal or deformation of material at solid surfaces. Causes of wear can be mechanical, e.g., erosion, or chemical, e.g., corrosion. The study of wear and related processes is referred to as tribology. Breakage due to overload. What load applied more than the capacity of machine element? Machine element fails in tensile, compressive, or shear forces on in combination of these forces. Breakage due to fatigue failures. Fatigue is a failure mechanism that involves the cracking of materials and structural components due to cyclic or fluctuating stress. While applied stresses may be tensile, compressive, or torsional, crack initiation and propagation are due to the tensile component. Distortion, due to excessive load or heat component twist, or these is change in shape and geometry of machine component. Creep, elongation of component, turbines, when working in normal load and high temperature. Erosion, it is a degradation of material surface due to mechanical action, often by impinging liquid, abrasion by a slurry, particles suspended in fast-flowing liquid or gas, bubbles or droplets, cavitation. Corrosion. Corrosion is the irreversible damage or destruction of living tissue or material due to a chemical or electrochemical reaction. Example. A prime example of corrosion is rusting of iron or steel. Oil degradation. Oxidation is the reaction of materials with oxygen. It can be responsible for viscosity increase, varnish formation, sludge and sediment formation, additive depletion, base oil breakdown, filter plugging, loss in foam properties, acid number increase, rust, and corrosion. Electrical motor insulation failure. The main causes of insulation failure are dielectric contamination, temperature cycling, excessive overloads, excessive voltage stress due to overvoltage, and aging. Electronics component failures. Failures can be caused by excess temperature, excess current or voltage, environment contaminations, mechanical shock, stress, or impact. Here, you can explore the key factors and events that contribute to component failures, categorized by their underlying causes. Atomic or microstructural failures. These arise from excessive compressive or tensile forces, leading to material deformation or fracture. Cyclic stress fatigue is another common cause, where repeated loading weakens the component over time. Manufacturing-related factors. Defects introduced during production, such as metallurgy or formulation errors or deviations in process conditions, can compromise a component's integrity from the start. Of operational stresses. Components experience various mechanical stresses during use, high-pressure conditions, improper bearing loads, either underload or excessive fits, and other operational strains that accelerate wear and failure. Environmental conditions. Harsh surroundings, such as corrosive environments, extreme vibrations, particularly in electronic installations, or thermal fluctuations, can degrade materials and impact long-term reliability. Life cycle considerations. Whether at the conceptual stage, feasibility analysis, active operation, or maintenance phase, a component's design and usage history play a crucial role in its failure potential. Each of these factors can significantly impact component longevity, making it essential to identify and mitigate risks early in the design and operational phases. Example of rotating equipment failures. Misalignment 35%, out of balance 30%, rolling bearings 7%, journal bearings 7%, electrical motor 5%, gear 4%, looseness 4%, resonance 3%, shaft bend 3%, blades 3%, oil whirl rub 1%. And few are mapped for life cycle stages, failure mechanism, and physical failure or modes. Example: misalignment of motor and pump shaft. The life cycle stage is during commissioning, As a failure mechanism, it experiences excessive cycle stress, and ultimately bearing fails due to fatigue. Let's understand what is overload and fatigue. Aging. Forces cause stress in the part when a load contacts the part. The smaller the contact area, the greater the induced material stresses. We show the pattern of varying operating loads that a part can experience at the contact points as a curve from least load to most load. Parts age as they're used. Loads stress the physical structure, and it breaks under high loads. The weakest parts fail early. The strongest take more stress before they too fail. We show the degradation as a curve of material strength from most strong to least strong. Why do parts fail? Because they can no longer handle the stress they suffer. When the load is too great, the part fails from overload. When the material weakens and degrades, it fails from fatigue. Keep stress low in your machine parts. We must know what our equipment parts are made of and prevent high stress in those with infinite life, but replace those of finite life before they fail. Using a factor of safety means the designer intended for the operating stress to be so low that it produced a long, trouble-free service life. We know that parts also fail from being overstressed. This overstress is imposed on the part. Each overstress takes away a portion of the part's strength. When enough overstress accumulates, or there is one large overload incident, the part suddenly fails. Wear-out failures are any failure mechanism that result from parts weakening with age and degrading usage. Included are processes involving material fatigue, wearing between surfaces/substances in contact, corrosion, degrading insulation, and wear-out in light bulbs and fluorescent tubes. Initially, the strength is adequate for the applied load, but over time the strength decreases. In every case, the average strength value falls, and the spread of strength distribution widens. This makes it very difficult to provide accurate predictions of operating life for such items. The degradation cycle shows the failure sequence for equipment parts. From normal operation, they go through recognizable stages of degradation. This is the basis of condition monitoring, which is also known as predictive maintenance. The degradation curve is useful in explaining when and why condition monitoring is used. Knowing that equipment parts show evidence of developing failure, it is possible to inspect at regular time intervals for signs of changes in behavior. The point at which degradation is first possible to detect is known as the potential failure, P point. The point at which failure has progressed beyond salvage is the failure, F point. We must condition monitor frequently enough to detect the onset of failure, so we have time to address the failure before it happens. In our continuous discussion about failure curve, let's examine the example of roller bearing failure curve, how failure deteriorates are re-technology driven. Roller bearing defect severity. Stage 1. Earliest detectable indication of bearing failure using vibration analysis. Signals appear in the ultrasonic frequency bands around 250 kHz to 350 kHz. At this point, there is approximately 10 to 20% remaining bearing life. Stage 2. Bearing failure begins to ring at its natural frequency, 500 to 2000 Hz. Signal appears at the first harmonic bearing frequency. 5 to 10% remaining bearing life. Stage 3. Bearing failure harmonics of the fundamental frequency are now apparent. Defects in the inner and outer race are now apparent and visible on vibration analysis of the noise signal. Temperature increase is now apparent. 1 to 5% of remaining bearing life. Stage 4. Bearing failure is indicated by high vibration. The fundamental and harmonics begin to actually decrease. Random ultrasonic noise greatly increases. Temperatures increase quickly. Remaining life 1 hour to 1%. You can also observe the best suggested maintenance strategy at different severity stages and sensitivity of measuring techniques in determination of defect severity. Cause and effect of our equipment failures. Infant mortality cause. Incorrect processes, controlled by management. Poor quality control in vendor selection and / or product progress monitoring. Error-induced zone. Defective parts. Poor assembly. Manufacturer error. Poor commissioning. Poor startup. Transport damage. Random failure zone cause. Induced stress, controlled by operational and maintenance staff. The stress-induced zone includes operating overload. Stress aging of some parts. Local environment degradation. Operator error. Poor operating practices. Poor maintenance practices. Poor design choice. Acts of God. Wear out zone cause. Accumulated fatigue controlled by operational and maintenance staff. Usage-induced zone. Many aging/used parts. Many parts degraded. Better materials. Considerate operation. Building for the physics of failure. The mechanisms of failure caused by stressing components has become known as the physics of failure, POF. The chart shows the best practice process now adopted in designing equipment following recognition of the influences and effects of POF. The parts are modeled by finite element analysis or other test regimes, and their behaviors analyzed under varying operating conditions. The probabilistic life cycle performance is identified under the various situations, and the results indicate the design limitations and operating constraints to achieve a desired failure-free life.